Welcome everyone to the Data Science Seminar Series. I'm David Bader, a distinguished professor at NJIT and also the director of the Institute for Data Science here at the New Jersey Institute of Technology. I'm very pleased to have our speaker today, Dr. Vipin Kumar from the University of Minnesota, who will be speaking on big data in climate and earth sciences, challenges and opportunities for data science. Today is also a Ying Wu College of Computing distinguished speaker for the spring 2021 semester. And I'd like to introduce the Ying Wu College of Computing Dean, Dr. Craig Gottsman, to introduce Dr. Kumar. Craig?
So welcome everybody. Welcome to this double feature. It's the weekly seminar on data science organized by David Bader. Thank you, David, for organizing this. But it's also the Ying Wu College of Computing Distinguished Speaker Talk, which we typically have once a semester. We had invited Dr. Kumar from the University of Minnesota to give this talk a year ago. He had agreed, fortunately for us, but unfortunately for us, we actually couldn't hold the talk as planned because of COVID, and we had to cancel it. So we're very fortunate to have with us today Vipin Kumar from the University of Minnesota, who will be giving the talk. He's our distinguished speaker for this semester. So let me tell you a little bit about Dr. Kumar. He's had a very distinguished career, still has a very distinguished career at the University of Minnesota. He's the Regents Professor at the University of Minnesota, where he holds the William Morris Endowed Chair in the Department of Computer Science and Engineering, where he also served as the department chair for many years in the past. He earned his BE degree in Electronics and Communications Engineering from the Indian Institute of Technology at Roorkee, and his Ph.D. in Computer Science from the University of Maryland in College Park in 1982. His research interests span data mining, high-performance computing, and their applications in climate ecosystems and healthcare. And his research has resulted in the development of a concept of ISO efficiency metric for evaluating the scalability of parallel algorithms, and for the development of highly efficient parallel algorithms and software for sparse matrix factorization and graph partitioning. Dr. Kumar has been elected a fellow of the AAAS, the American Association for Advancement in Science. The AC, he's a fellow of the ACM, a fellow of the IEEE, and a fellow of SIAM. He has also received a Distinguished Alumnus Award from the Indian Institute of Technology and many other awards, including the Innovation Award at SIG KDD 2012, which is the highest award for technical excellence in the field of knowledge discovery and data mining, KDD. He's also received the 2016 IEEE Computer Society Sydney Fernbach Award, one of the IEEE Computer Society's highest awards in high performance computing. Let me just mention that I'm familiar myself personally with Dr. Kumar's work. As I mentioned before, he has written together with George Charybdis the Metis library for graph partitioning. I've used it myself for the last 20 years in many, many different occasions. I can tell you from firsthand experience, it's an excellent package. It's very efficient. It's scalable. It does an excellent job, and it served me very well over the years. So thank you, Dr. Kumar, for that. And actually, I'm still using it every day, both in a variety of software programming environments. I myself work in computer graphics and mesh processing and so on. Therefore, it's very relevant and very helpful in that context. So without further ado, I'd like to invite Dr. Vipin Kumar to deliver his talk, Big Data in Climate and Earth Sciences, Challenges and Opportunities for Data Science.
Thank you very much, Craig and David, for inviting me, and it's a pleasure. So my talk is about the big data in climate and earth sciences, effectively seeing how the data revolution that has changed all aspects of our life could also help us address some of the environmental challenges that are growing and need to be addressed in a very timely fashion. So just a little bit of an introduction, what are the environmental grand challenges of the 21st century and why it is so critical. And again, we are living through the pandemic for the last almost 12 months now. We have been in lockdown nationally, internationally. And we are, one thing that sort of is clear living through the pandemic is that it's a problem that requires everybody to solve together. It's not a problem that I can solve by myself or a country can solve by itself. It's if if it exists anywhere, it exists everywhere. It can sort of come back to haunt everywhere. So basically, there are certain problems on a societal scale that require global cooperation. And we have a taste of it from the pandemic. And there is a much bigger sort of problem that is sort of unfolding in front of us, and slowly over a period of, literally decades and over a period of, 100 plus years. And just like in the pandemic, the actions you take have a delay in the response. You do a lockdown today, the cases start coming down a few weeks later or a month later or 2 months later. And similarly, you become careless, and then the impact is seen many, many weeks later. So similarly, we have a situation here where the problems that we have are delayed response to the actions we have been taking. And any action we take now would not necessarily have an immediate response. So this is sort of a COVID effectively is teaching us how to basically get ready for some of these grandest challenges that literally may be impacting our survival as a humanity. So there are multiple components of this, and I just like to sort of start with the climate change. And climate change, of course, has been on the radar of the scientific community for at least 50 years. And but increasingly, it's becoming more and more clear that there's an urgency to solve this problem, because in the beginning, the understanding was that maybe the worst effect of climate change would be seen well into the future, like 2100. And of people at my age, I could care less what happens in 2100, right? Or I could sort of pretend to care less as to what happens in 2100. But more and more, it's becoming clear that many of these problems are going to be hitting us sooner than later. And actually, we are already seeing many of these problems occurring in front of us. This is just a picture, image sort of showing the European heat wave in 2019. 2020, by the way, was the Europe's hottest year. It was, so there is no let up in this game. The 2020, of course, globally is also ranked as the warmest year, along with 2016. And what makes it worse is that the 10 of the hottest years have happened all in the last 15 years, in the sense that we have changed the global average. And now this changing climate is not simply only impacting the temperature, but also impacting everything else that you're seeing around you. There's more moisture in the air. There are more snowstorms of the kind that you experienced a few weeks ago. There are hurricanes that don't move as fast. They dump a lot of water. So it's sort of manifest in many, many different ways, and it's sort of it's a problem that needs to be addressed globally, and perhaps with a long cooperation which should be even more intense than the one we are seeing for the pandemic. Now, the climate change is not the only environmental grand challenge that we are facing. There is another grand challenge that is also progressing at a certain rate, and which is sort of causing us to sort of figure out how do we feed the world without destroying the planet. And let me just give you a little bit of a sense of what's happening there. So if you look at the world's population, sort of beginning from the dawn of the civilization, let's say about thousands of years ago, before starting from the farming revolution, the population of the entire globe was about 500 million people, approximately. And it remained that much. It will grow a little bit, shrink a little bit. And then starting about 150 years ago, it started to increase. And by the turn of the century, we had about 6 billion people on the planet. About 10 years ago, we had 7 billion. We have more than 7.5 now, and increasing. And of course, we might saturate at as much as 10, 11, 12, or 13 billion. So population is increasing tremendously. People's dietary requirements are, of course, changing. Back 100 years ago, very small number of the people in the world had much to eat. Only a small number of people were well off. Now our goal is to make sure that everybody eats well and everybody has proper nutrition, which means the nutrition demand is also increasing. So the scientific community sort of expects that the amount of food that we need to feed the growing population, which is going to grow by about 50%, might actually go up by as much as 100%. And all of this increase you're seeing is in the last 50 years or so. Basically starting about 56 years ago, the population explosion really started happening dramatically. And if you look back at 56 years, and see how we have responded to be able to feed this growing population. We have done three things. We have cleared more areas that are forested to make land for agriculture. That's one thing we have done. We have used more irrigation. Irrigation used to be very, very limited, prior to 1950s and 60s. Now, more and more land, more and more agriculture is irrigated. Basically, you use the water to irrigate it, and then we use more fertilizer. And each of the three approaches that we have used to feed the world, from a couple of billion people, let's say about 70, 80 years ago, to almost 13 and a half or 14 billion people today, 7 times more, 5 to 6 times more people that we are feeding. We have handled this by these three approaches. And all of these three approaches are getting into serious trouble. And number one, converting forest into agricultural land. That's no longer looking like a feasible solution, partly because we've already converted more than half of the tropical forest into the agricultural land. There's not much more left land to the forest land to turn into agriculture. And the second thing is the forests lock a huge amount of carbon just by being there, and converting them into agriculture releases a huge amount of carbon, which is very hard to replace. So it has a very direct impact on the climate change. So that's a big interaction there. That is, if you want to feed more people, and if you're willing to cut more forest, then of course you're making the climate change problem worse, substantially worse than what it is. The second thing is water. The availability of water under the changing climate scenario is becoming a lot more uncertain and irregular, in the sense that the amount of water, of course, that's going to fall on the earth as a result of climate change is going to be more, but more of it is falling in smaller durations. That means you have a lot more floods of the kind that you sort of read the newspapers, and you have more of the drought. So you can always see in the same state, multiple counties, some counties having floods and some counties having drought. So this is becoming a very serious situation. And of course, this problem is compounded by the fact that the humans, of course, also need the water for agriculture. So you're seeing a major environmental disaster on this picture here on the top bottom right side. If you look at this is on the left side of this image is the Aral Sea in 1989. And Aral Sea is the largest freshwater body in the Asian continent, very, very massive body. And this is how you look in 89. And this is how it looks on the right side in 2014. So about 25 years later, you see very little piece of it. And what happened here, this water body was fed by 2 different rivers. The water from that was diverted for agriculture, for good intention. And then of course, resulted in ecological disaster, which changed the microclimate of the region and all sorts of effects that sort of happen afterward. So, and problems like these are becoming worse because not only we need more water for the growing population and for growing more food, but the water supply itself is becoming uncertain. So there's a big challenge there. And the third thing is the ability to, the fact that we have been using fertilizers to grow our crops is actually also creating a lot of trouble for our waterways, our lakes, and our oceans. And what you're seeing here on the bottom left picture is the algal blooms, the harmful algal blooms that sort of spring up in lakes and water bodies and in the deltas of the rivers, just because we have been dumping too much fertilizers, basically the fertilizers that are sort of being used in the farms in the neighborhood of these lakes, the runoffs from those farms sort of ends up coming into these lakes and then creates this ecological disaster, which means when you try to drink that water, people could die. And of course, this is, you see this glass of water, this green stuff is not a smoothie, it's the water out of the lake, which of course is very poisonous, dangerous water. So all of these problems are sort of coming together and again, they need to be solved. They need global cooperation. And they have a time scale, which is, of course, much, much slower than the pandemic we're looking at. These problems happen at yearly, decadal, century scale. And then you have to sort of take decisions to be able to address them. And there's a huge community of scientists in multiple disciplines whose job is to sort of study these problems and then try to figure out scientific methodologies for addressing them and, of course, inform the policymakers. the question that one sort of can ask is, what about the folks in data science? What's about the data science community? What does it have to do for solving this problem? And that's the focus of my talk. If you look at it from the data science perspective, of course, this slide is, of course, just telling you what we're living in. We're sort of living in the golden age of data science. Data revolution started about 50 years ago and has allowed us to collect more and more data in all walks of life. And this revolution is accelerating. It has sort of become even faster in some sense of growth in the last 10 years, in the last 5 years. And you can see that the development of the kind of confluence of high performance computing, the large amount of data that we're collecting, and the novel methodologies for analyzing these data sets, in this broad field of machine learning and AI is sort of coming all of this together. And they have changed everything we do in life. They're hugely successful in commercial applications, and you're able to do things that you could not have imagined just 5 years before, 10 years before. Even the way we are living through the pandemic today is made much easier because of the revolution of the data revolution and the data science. Now, now this revolution that has happened broadly in the society has also been happening in the environmental sciences. 40 years ago, satellites were launched, but about 45 to 50 years ago, the first satellites were launched, and they started taking pictures of the Earth, which gave a lot of information about the environment. And increasingly, over the period of last few decades, and especially in the most recent decade, a huge number of satellites are operational, and they're giving us more and more precise picture of the Earth and its environment at a scale in both space and time that could not have been imagined just a decade ago or a few years ago. And what you're seeing here in the animation on the top left corner here is the animation of one of the instruments called MODIS on one of the satellite from NASA. There are two satellites, Terra and Aqua, that has this instrument, and it takes a picture of the Earth every single day. So if you look up the sky and at the NJIT campus, you look up and you look up at the sky at 10:30 a.m. This sensor is sort of going over your campus and taking a picture. Every day, every pixel on the Earth is pictured at least once. And these images, of course, are mosaicked. You have this space-time data available that is being pre-processed automatically by the scientific community, actually by the contractors from NASA. And then you can use that data and, of course, see it in the spatial framework or a temporal framework, or, of course, analyze it in both space and time. So, for example, if you look at a specific time of the year and you look at the data and as a composite, you see this picture, and if you only look at the greenness of the pixels, you can, it's a composite which is made of multiple bands that are sort of collected by the satellite and converted into a single variable called vegetation greenness. And you can see, just by looking at this image, you can figure out where are the dense tropical forests in the globe, where are the deserts, and of course, you can also imagine by just looking at this picture that it must have been taken in the summertime, because I live in Minnesota, and Minnesota is all white at this time, and when you look out the window. Or if you look at a single pixel on this globe and look at how this greenness is changing, you have this time series that you're looking at. This time series actually is taken from the location of the China National Convention Center. And by looking at this time series, which is the annual time series starting in 2000, and you can see the annual cycles, and you can actually imagine, by looking at this time series, you can figure out that this convention center must have been built in around 2007, 2008. And of course, what happened was, this is the location where the Olympics were held in Beijing in 2008. This area happened to be a farming land. And then around this time, a couple of years before the Olympics, these farms were cleared, and of course, the rest is history. So what I'm saying is that by looking at these images in both space and in time, you can learn a lot about what's happening. And this data, of course, is coming from MODIS, but MODIS is just one of the many, many satellites. Of course, it gives you global coverage. Landsat has been sort of giving coverage of the entire Earth every 16 days at a finer resolution of 30 meters, going back to basically in 1980s. There are other satellites. For them, Europeans have launched a series of satellites called Sentinel 1, 2, and 3, and then they provide global coverage of the Earth at 5 meter, and in some cases in 10 meter resolution, giving you almost 8 trillion pixels on the globe with 12 different bands. It's a massive amount of data. And there are commercial organizations who are able to watch the Earth at centimeter resolution. That means you can see people walking, you can see cars, you can see, and many of these data sets can even be on a daily scale. So you can imagine all kinds of commercial utilities of these data sets, and of course, in addition, the environmental one. So this is a huge industry. It's a huge and fast-growing industry in terms of how do you analyze the spatio-temporal data sets about the Earth and its environment. And of course, a lot of it is environmental value, but a lot of it is also has just plain commercial value. So the purpose of my talk is to sort of give you a sense of what the advances in data science, along with these very interesting data sets, allow us to address some of the grand challenges in the environmental sciences. And I'll give you 3 sample case studies. And the second thing is that when you try to address some of these grand challenges in environmental sciences, you run into problems that the traditional methods that you have, that they work very well in the commercial domains, actually do not work very well here because of the nature of the data, which is both varies in space and time, and a huge amount of heterogeneity. That is the phenomena that sort of happens in one place is very, very different in both space and time and at different places, and you will see examples of that. And the fact that the amount of labels are very hard. The label data, training data, can be very, very hard to collect and very expensive, and could, because of the heterogeneity issues. And so it requires development of entirely new approaches. And these approaches, of course, are aided by the fact that these phenomena, environmental phenomena that we are looking at, is actually these are physical, biophysical processes that are unfolding, and you're watching them from the satellite or from other sensors. So if you leverage the underlying physics of the physical process, of the biophysics of the physical processes, you have an opportunity to address some of these challenges. So basically, these challenging applications force you to think differently about data science solutions. And as a result, you come up with novel approaches that can come back and revolutionize the field of data science itself. And in fact, a lot of the work that sort of started here in some of these problems is leaning to new direction, sort of feeding into new direction. And that's very becoming very popular and very common, which is sort of called the scientific knowledge guided machine learning, or you can call it sort of physics guided machine learning, where you're not treating the problem that is being solved by machine learning as a black box, but you're sort of saying you're trying to emulate a physical process, and understanding the physical behavior, of course, gives you more insights into how to sort of model it using machine learning. And it has applications in literally every single branch of sciences. So here, again, coming back, I'm going to talk about 3 different problems. In each one of them, I'm going to talk about the significance from the environmental perspective, but very briefly what the challenges are, and very briefly as to what we did to solve them. And to motivate you that these are really interesting things that can be done and can be done by the students and researchers in data science. I'm going to show you some results on global scale. So sort of to show you that yes, being a data science researcher, data science student, you can actually have an impact on a global scale. So the 3 problems I'm going to talk about, as I said, it will be very high level talk, would be one of them would be being able to map the forest fires on a global scale. And why is this an interesting problem? Because forests, just by being there, by their natural growth, are able to absorb so much carbon. They're actually a carbon sink. They're they're one of the cheapest way and a natural way to absorb carbon, the carbon dioxide from the air and into sort of their roots and the leaves and so forth. But so they cover about 20% of the carbon budget for the planet, which is about as big as the entire transportation sector. Every single car, plane, ships, train, and everything put together emit as much carbon as it is absorbed by this forest just by being there. Okay? So it's an amazing sink of carbon. The only problem is that the same amount of carbon gets emitted from these forests just by these forests getting burned or degraded. So, so being able to figure out one of the biggest goal for the scientific community or the global community is on which everybody is in agreement, is that we need to save this forest. Because if you can reduce or eliminate the degradation and burning of this forest, you have you have an automatic ability to absorb a whole bunch of carbon, a lot of carbon, just from the forest being there. Okay? Now, to be able to do that, of course, you need to require the ability to monitor these forests, so you can incentivize people to not burn them, not degrade them. And it turns out that because of the ability, because of the heterogeneity and a number of other issues, including the fact that there's a rare class problem, you need to design entirely different kinds of algorithms. So there is a series of algorithms that develop. We call it rare class prediction in absence of ground truth, which I'm going to show you results of that approach on a global scale. The second thing is, a lot of these forests are burned and the area gets converted into plantations. And one of these plantations that the people have been planting there for the last 20 years is the oil palm plantation. And the initial intent 20 years ago was to convert this forest into oil palm plantation, use the oil palm as a biofuel to give a renewable energy source. And it turned out pretty quickly that this is actually not a very viable option. Once you convert this forest into plantations, you have actually emitted as much carbon as you would probably might save in, would require at least 100 years of the cycling to save. And again, you've done a huge amount of ecological disaster. So, so basically, and oil palm is used so extensively even beyond the fossil fuel or the biofuel. It's, if you open your pantry anywhere in the world, almost everything that you have in your pantry has some amount of oil palm, and it's coming out of these forests that have been deforested, and you see this forest being converted into these beautiful oil palm trees. So some of the largest corporations in the world have promised not to source anything from these recently deforested lands, but then you don't know exactly what locations are deforested and what locations are not, because when you look at these oil palm plantations from the sky, from the satellite, they look so green that they look like real forest. So how do you figure out the conversion of the forest to the plantation, going back in time, so you can figure out which locations were converted recently versus much earlier, and you can penalize people to not deforest these lands any further. That's the second problem we're going to talk about. Again, it required a whole bunch of innovations to address this problem. The third problem I'm going to talk about is being able to map the surface water dynamics. And as I mentioned to you earlier, that because of the changing climate, the availability of water on the Earth has become very uncertain. Some places you will see basically huge amount of downpours leading to floods, and many places you will see floods. And again, you can see the example of the two different pictures here on the right side, right bottom side, and you can see the same location, a river, that Colorado River that's being so wide and rich, sometimes becoming very, very tiny, in the sense that you can see in the drought condition, these rivers and waterways can shrink pretty dramatically. And it leads to all sorts of water scarcity down the chain. So being able to understand, have a good handle on the stocks and flow of water on a global scale can make it easy to solve a whole bunch of ecological problems. It can help in planning, it can help in flood monitoring, it can help in drought management, it can help with the agricultural and all sorts of things. And the ability to even this monitor service, but has been very, very limited, despite the fact that in year 2000, NASA launched a special mission of the space shuttle just to locate water on the Earth. So basically, it's it's important enough problem that people have launched missions. The agencies have launched mission just to create such information. So these are the three different problems I'm going to talk about. As I said, there'll be my solutions. I will briefly talk about the challenges, why these problems are challenging, what new methodologies got created very, very briefly, and show you some results. And hopefully that will sort of motivate you to look through some of these problems more deeply. And of course, on our website, we have many, many papers on each of these topics and more for you to get deeper understanding. Okay, so the number one, let me just go through them one by one. So the first problem is about being able to map the burned areas, the burnt forest on a global scale. And it might seem like a problem that would fit very well into the traditional predictive machine learning framework, like the traditional classification framework, because you can look at satellite images and you can sort of look at the forested area, like what you're seeing here on the bottom left screen. You see the area is quite green, and there's a portion of it is just brown. And if you look at this picture, you can very easily figure out over a period of time that this area was green in a few months before, it became brown, and then a few months later, it became green again. It must definitely be a forest fire. You can sort of say in many cases with a great confidence that these regions must be the burnt areas on certain dates. And if you have that information, you can create training data sets in which the training data set has the variables, the attributes. These are vectors, of course, the satellite vectors on specific dates for different locations. And you can give them labels for those locations to be either true or false, that is burnt or not burnt. And once you have a large enough training set, you could apply this. You can build a classifier and potentially apply it anywhere. The only problem here is that when we are sort of trying to really handle the mapping of especially the tropical forest fires, we have to treat this problem as if you don't have any target label for supervision. Okay, and the reason is that labels are available in the world for forest fire, but they're very limited. So if you go to California, which is of course suffers from a lot of forest fire, the state of California produces near perfect ground truth each year. So you can go to the website, the state of California website, and download the polygons, which sort of tell you in each year which areas burn. Canadians do a pretty decent job as well. They have a lot of forest fires. Rest of the US, we have some product, not very good quality. Rest of the world, they're in a pretty bad shape. And the portions of the world, which is the tropical forest, like the Amazons, the African forest, and the South Asia, this region of Indonesia, Malaysia, we have extremely poor information there simply because these areas are very, very hard to watch using satellite the way I just talked about. If you look at the images of the satellite, a lot of time they're cloudy, and a lot of time when the fires burn, they create so much smoke that the smokes actually can travel for miles and stay there for weeks, and the image can be completely cloudy. So the traditional approach of creating ground truth in these middle areas actually becomes even harder to apply, because in places like US or even in Europe, if you really wanted to create a good ground truth, you could do it by investing enough money. But in these places, simple brute force dumping of money isn't going to do it, which means you need smarter algorithms. That's one problem, that you have to teach this as a complete absence of target label for supervision, because the labels that are available in California, and if you build a model using those models do extremely poorly in other part of the world, and certainly in the tropical world. And we are going to get around this problem of having no labels, again, by utilizing the fact that these fires, when the trees get burned, this is just one aspect of the burning that you're seeing from the spectral signature. The process of burning actually creates heat, and the heat is also visible from other sensors, which is, of course, not necessarily perfectly matching with the forest fires. It's called the thermal anomaly. So you can have, because there's a physical process, there could be multiple proxies for the same process, not all of them being equally good. They could be very, very loose proxies, and yet the ability to use those proxies would help us build better predictive model. That's what you're going to see in a few minutes. So that's one challenge we're going to see. And the second challenge that we have here is that these, anytime you're looking for things like, changes in the land cover, they would necessarily at a given time step would be of a rare class, in the sense that in any given year, the most recent year for California forest fires was very, very strong, one of the worst years, just like the 2008 year of 2008, and about 3% of the forested area burned, which is a large area, a large amount of area, but which means that if your algorithm is making a small amount of error, if you have a small false positive rate, you could have very, very poor performance in a highly imbalanced scenario. So which means you have to actually worry about dealing with imbalance in your predictive modeling, in addition to the fact that you don't have proper labels. Third challenge, of course, you have is that when you are looking at things like tropical forests, and you do not have the ability to evaluate, you don't have the ability to get golden ground truth, it's very, very difficult to evaluate the performance of the imperfect labels. So all of these challenges sort of came together. I mentioned to you, build a methodology, and it's a multi-step methodology. It's a pretty complex methodology, and I'm just only going to talk about one component of the methodology. This is the only technical component of the talk, and that is what we're talking about is a situation where I would like to have perfect labels, golden ground truth, which would look like this. I have features and I have labels. And some of those features are positive, blue, and negative, let's call them red. And if I had the perfect labels, I will be able to build a traditional machine learning model. But in reality, what I have is imperfect ground truth. That is, a lot of these gold ground truth labels have been corrupted. And let's assume corrupted by a random process. Some of the blues have become red and some of the reds have become blue. And so alpha and beta are the probability of sort of these corruptions. And these are the imperfection labels. This is how we're modeling them. And the idea is that under what situations can I build a good model given imperfect labels? And of course, as I said, for the environmental problems, the imperfect labels come from the other proxies of the environmental phenomena. If you're looking at the burned area, looking at thermal anomaly. If you're looking at urban settlement growth, you could be looking at nighttime lights. But if you're working in the commercial problem, of course, the same solution that we're talking about could work. For example, recommendation of an item to a new user. You may not have that information, but maybe you have information about their friends' interest. Maybe that could be helpful. So these are sort of the kinds of things we're talking about. That is, building a framework that can work with this scenario as opposed to the ideal scenario, in the context of course, imperfect labels and so forth. And this slide sort of just puts this whole thing into the broader perspective, that there's a whole rich field of supervised learning in machine learning. Most of it involves starting with expert annotated labels, the labels that you can trust. And if you have many of them, nothing is needed further. You can use off-the-shelf algorithms, including deep learning algorithms. And if you have plenty of samples, you can build a really, really good model. If you don't have enough training samples, then a whole series of methodologies have been developed in machine learning that can help you to work with that. But what we're talking at is a situation where I have only imperfect labels. That means I have no gold standard ground truth. Now, even in this context, people have dealt with situation where you have multiple annotators. That is, you have multiple labels, multiple sets of labels. Each label is imperfect. For example, you might sort of think of this arising in the mechanical terms. You can have images being labeled by different people, and as long as each image has imperfect annotation from multiple annotators, there are techniques that you can develop to learn from that the exact label, because you can assume these annotators are making mistakes that are uncorrelated. Of course, we don't have that situation. Physical processes do have proxies, but they don't have too many proxies. Typically, we're looking at, let's say, one proxy, so single annotator. Even here, people have built situations in which you have partial supervision. That means you have corruption only in one of the labels, but not the other. So you have corruptions in the positive, but the negatives are perfect. For example, you have some positives that are known to be perfect, but some of the positives became negative, and of course, all the negatives are negative. Now, that's it. But the situation what we have is actually not of a partial supervision, but the imperfect supervision. And even here, people have dealt with a situation in which these positive and negative classes are balanced. And again, we have a rare class situation. So basically, we're looking at this entire hierarchy, being able to map these tropical forest fires is looking at a very difficult subset of this entire space. But the solution that we built here for this corner here actually built on the successes that people had, solutions that people had built on each one of these other three threads, in some cases going back to the work as far back as 25 years ago. Some of the earliest results in this area, in theoretical sense, were published in 1995. Some more work got done in the 2000 and so forth. And by building upon all of them, this technology methodology was built, and which has become very powerful and able to give results on a global scale. For example, for this tropical belt that you're seeing here, where most of the tropical forests are located, the state-of-the-art product from NASA provides certain amount of locations that they think have been burned in the last, in the past years. And people, of course, scientific community knows that those are gross underestimates. So this is a well-known fact. But our product generated using this new algorithm was the first product that was able to provide a very comprehensive view, which was much, which effectively about 3 times as much area that was burned. And of course, it went through a very rigorous evaluation process to sort of convince people that it was really, really good. So this is one, and again, this is a visual illustration of anecdotal evaluation. Of course, the technical paper, of course, had a much more thorough evaluation. Here, what you're seeing here is the location in Brazil, in the Amazon rainforest from year 2000. So you can see just the satellite imagery here on the left side. And you can see it has some clouds, which just happened to be, the image happened to have some clouds on that day. And then you can see some of the area that is deforested, which is the white area. We can see, if you look at closely, you'll find these are all the deforested area. Now, if you look at the same image in 2015, this image happened to be cloud-free on 2015, but all of the white stuff that you're seeing here is all deforested land. And imagine each little tiny pixel on this image is a square kilometer. So this is a very, very large area. And on the very right-hand side of this image, this very last one, is actually this image in the middle. And what we're doing is we are plotting all the locations that our algorithm called to be burned. And of course, it has 2 different colors, yellow and green, yellow and red. And the yellow and red are the locations that were found by our algorithm. And red are the locations that were found by the NASA's state-of-the-art algorithm, which means you can sort of see that how little of this entire area was able to find as burnt area. And you can see all of these features that you can see here. It gives you a sense of how these areas get deforested. Basically, you take the forest, you burn pieces of you build roads, and you build the area around them by burning them, and of course, they become forested land. So this sort of gives you a sense of the entire dynamics of this area. Second thing I'm going to sort of very quickly mention is this being able to map the dynamics of plantations of the tropical forest. As I mentioned earlier, it's a huge problem. Some of the biggest corporations in the world would like to stop sourcing product from the areas that have been recently deforested. But given the importance of the problem, people have sort of tried to figure out products which would sort of tell you which area was forested, was converted from forest to plantation. At what time. So there is an organization called Transparent World, which built this map for a portion of Indonesia for year 2014. Each of the red dot is supposed to be the area which got converted from forest into plantations. The only problem with this product is it's only from 2014. And it has lots of errors. That means a lot of the locations that are red actually are not converted. Many of them are, but a huge portion of them are not. So there's another organization called RSPO, Roundtable on Sustainable Palm, which created a map for 2001, one for 2005, one for 2009. These maps are much more precise, but hugely incomplete. That is, in each of those years, there are many, many other locations that have been converted from forest to plantation, but the maps don't cover that. So again, there are a lot of challenges here, as I said, most of them relating back to the heterogeneity and the algorithm, machine learning algorithm, had to be built that sort of took the entire underlying process into account. And as a result, we are able to now see this dynamics of conversion from forest to plantation, and of course, as an evolution in time. So if you look at these three images, the animations, the red locations are plantations as of oil palm plantations as of 2001. And if you focus on these dates here, you will see them changing. And as they're changing, the green areas are sort of increasing, 2001, 2002, 3, 4, and you can sort of see them green. So you have, for the first time, you have a dynamic view of the entire plantation. And why, of course, this is good, because one, of course, you will know which area got converted when. And if people sort of know that somebody's watching them, then maybe they will be less inclined to convert more of the forest into plantations, because they may think that people will not buy any products from this area. Now, there's one more utility of what we are talking about, what we're seeing here, connecting it with the previous work on forest deforestation that you can sort of see here. And that is, if you look at these locations that have been deforested to convert into oil palm plantation, and from over a 15-year period, 2001, 2014, each of the green pixel is all of the plantations that are there in this over a 15-year period. Now, once the government of Indonesia gives people license to create these plantations, they're supposed to cut the trees, move them, and then convert the forest into plantation. But a lot of time, people find it much more expedient to simply burn the trees, because that's the fastest way to clear them, and then put the plantation, which is, of course, a ecological crime. Now, if you imagine how many of these locations actually might have been burned as opposed to converted by cleaning, I'm going to show you now, because we have the previous product from the previous case study. I'm going to take some of these pixels and convert them into a different color, red, which will tell you that a lot of them got burned. So you can see here, a lot of these areas got burned. Yeah, more than half of these pixels actually were burned as opposed to converted in the plantation in a regular way. But imagine if you are an area like this, and if you're burning this area to create a plantation, the fires do not have any boundaries. When you start a fire, it's very hard for you to sort of tell the fire to stop at the location that you are interested in. And on the next slide, I'm going to show you how many of these areas actually got burned as a result of some of these plantations. So you look at these blue areas. All of these blues are the unintended consequences of burning. That is, you wanted to sort of build a plantation. In the process, you created fires, which happened exactly. And of course, we know it because these areas got burned, and they got burned on the same date, around the same month when these plantations were built. So you can sort of see exactly the amount of damage that was done by many of these plantations. So you can sort of do the monitoring. You can sort of create actionable information, and hopefully it could give the government organizations or nonprofits to sort of enforce some of these regulations a little bit better. The last thing I'm going to talk about would be being able to map the water dynamics on a global scale. And as I said, it's coming under stress, not just from the changing climate, but also because of the human actions. And again, despite the fact that we have data from space shuttle from one of the months, February of 2000, for where the water is, there is a tremendous challenge for using the data for using traditional machine learning algorithm because of heterogeneity in space and time. What you're seeing here on the image here is the false color composites of these locations, 3 of the bands basically being converted into red, green, blue, and you're looking at the images. And now you can look at this, how the different colors, how different the colors are, which means the land and water in the spectral space at different locations and different times can look very different. And the image on the right side is actually sort of showing you that in many locations in the world, the data can be so bad that it's not even visible. So anytime you see a red color, actually the data is actually not even visible. So when you have a situation like this, it makes it very, very hard to build an understanding of how the water surface body may be changing. So again, by being able to incorporate some of the physical laws and other processes into the machine learning framework, we had to build some entirely new machine learning methodologies, and that has resulted into a system for monitoring surface water changes on a global scale. And it's available, information is available at multiple levels. What I'm showing you here is on the MODIS scale, which is each pixel is about 500 meters on each side. That means, and then of course we have information available similarly at Landsat scale, which means each pixel can be much, much smaller, and then so forth. So there are a series of products that we have in this case. But very quickly in the next few minutes, what I'm going to try to give you a sense of for this water body viewer is what are the different things you could do even from this very coarse water viewer. You will be able to see the surface extent of all of these large water bodies, which are at least 2.5 kilometers large on a global scale. And then you'll be able to see melting of the glaciers and lakes. You will be able to see local and regional change analysis, changing river morphologies. You'll be able to see reservoir construction on a global scale, and all sorts of other things that are very important from an ecological perspective. So if you went to the viewer, you will see little dots which sort of represent the water bodies. Each one of them, for example, represent the Don Martin Dam in Mexico. The viewer also allows you to see the time series of how big, how many pixels this water body has on a different date. It starts, of course, in 2000, which is the initial launch date of MODIS. And you can see that this water body happened to be, on some dates, it's as little as 100 pixels, and some days it's as large as about 1,000 pixels. So this water body has been growing and shrinking. And if you wanted to verify this, in some cases, you can see the time-lapse image from the Google Earth engine, which would, if you look at this image animation, which is yearly image, you'll be able to see that this image sort of matches the yearly product that we're giving the time series. You can look at this on a global scale. You can look at each pixel, each water body, and see whether it's growing or shrinking. If it's growing, let's say we make it red. If it's shrinking, let's color it green. Then you can certainly see some patterns. You can see some areas that are only red, some areas that are only green. For example, this is only green. Let's take a look at this one. And it turns out a very large area, thousands of square kilometer area in Argentina, in the agricultural land, has a whole bunch of green spots only. And these green spots actually have, at one time they used to, total water here was about 10,000 pixels, which is almost 2,000 square kilometer of surface water. And now, more recently, it has just shrunk and disappeared. And of course, if you look at a single water body, and it turns out that any one of these water bodies, this is a very large water body there, and yet it is shrinking quite a bit. So there is, this is the agricultural use of this water probably has resulted in some of these changes. If you look at other part of the world, you see a whole bunch of red spots. This is the Tibet, which is the area which has a whole bunch of glaciers, and the rivers from these glaciers actually feed about 2 billion people on the earth. In all of China, India, all of South Asia, all the rivers that sort of flow into this country originate out of the Tibetan plateau. And these glaciers have been melting, and this melting water is getting collected into the lakes that are formed inside the mountain cavities. And you can actually see them using this product. You can sort of see all of these lakes, all these little red areas are the extended areas, and you can see the Google time-lapse image to sort of show you how this area sort of increased over this last few decades. And because of this product, you can actually see on a global scale, on an aggregate scale, in the entire region of Tibet, almost 40,000 new pixels showed up of new water, which is almost 10,000 square kilometer water. There's a lot of water bodies that sort of showed up there. You can see the rivers dynamics, the rivers meandering, something the ecologists and hydrologists like to study, but they used to study them one at a time. Now using the system, you can sort of see them all on a global scale. You can see the impact of rising surface water. You see this area here in this picture here. This is the blue area is the one that sort of are the new pixels of water that have shown up. And you can, if you watch this animation, you will see that's where Google time-lapse is, of course, confirming it. You can see the presence of new dams being constructed, because when a dam gets constructed, the water body has a very small size before and very large size afterwards. So just by looking at the dynamics of water body, you can actually create a good history of where the water bodies have been formed. And as a result, we can actually build a global history of dams all over the world. Knowing about dams actually is of great interest to the community. So there is a database called GRAN, which the hydrological community maintains. This has, of course, thousands of dams. but small number, only a small number since 2001. And here are the 35 dams it had since 2001 in an earlier version that was until about a year ago or so. And you can see very small number of dams here. And using our product, we can, of course, figure out very quickly much larger number of dams automatically. Another bigger product we have, which has about 750,000 water bodies in this part of the world, which is below 50 degrees. And this collection of data that we have here is 3 times larger than the largest water body data set available to the scientific community. And not only we know about these water bodies now because of this work, but also know their dynamics, how they have been changing, growing, shrinking, and so forth. So there's a lot of ecological work that sort of can be done using this methodology. So with that, I'm going to sort of conclude. The result that I showed you are sort of a result of a series of environmental projects. One of them happens to this expedition project on understanding climate change, environmental changes using data. And there are many components. I talked about only one of them, which is the monitoring of the ecosystem disturbances. And as I mentioned earlier, that a lot of these threads of directions have led into this new direction of work in which I'm bringing physics and data together, and I'm bringing the machine learning and the physical sciences together to come up with the new methodologies that can give you new insights. Here are some of the papers sort of and news stories that sort of came out of this climate expedition, and just like to finally conclude that yes, indeed, big data in the climate and environmental sciences offer great opportunity to increase our understanding of the Earth's climate and environment, but they also offer us to create method advances in machine learning. So it's a very synergistic situation. That is, by advancing climate science, we can also advance machine learning. So with that, I'm going to stop and thank my collaborators and my students and former students, and take any questions. Thank you.
Vipin, thank you so much. It's incredible to see how much data science has advanced in terms of helping earth science and existential problems like climate change. So if there are any questions from the audience, you can use the chat or you can ask them here, but maybe I'll start by asking a question. Earlier in the talk, I was pleasantly surprised to see all of this work with the MODIS satellite. And about 25 years ago, as you probably know, I worked on ABHRR and MODIS algorithms, which was big data at the time with NASA when I was a postdoc at University of Maryland. And there we're using supercomputers like the Goodyear MPP, the convex exemplar. And I remember ABHR's 20-year history needed about 3 terabytes. Today, we could probably put that in our pockets, but at the time we needed a football field filled with supercomputers and data storage. What is the technology like today in data science? How big are the data sets, and what do you use to process them?
So as I said, ABHR is the first satellite that we started working with in 2003. We created the first global history of changes on the ecosystem from 1980s to 2000, back in 2003. But the MODIS, of course, is much bigger, and it already needed us to work with our supercomputers. Landsat, of course, is much larger, and the Sentinel has 1 trillion pixels on the globe. So once you get to the 10 scale, you're completely hopeless if you're working on the traditional environment. So you're looking at in our case, we have been fortunate to have access to the supercomputing at the Minnesota Supercomputing Institute, which has world-class supercomputers, very strong collaboration with NASA, which allowed us to work with NASA's Earth Engine, and again, collaboration from Google, which allowed us a fairly almost unlimited amount of computing on the Google Cloud. And all of that, of course, is absolutely critical. Just to give you a sense for this data set that we are producing for dynamics of the surface water bodies, it has required us to have almost about 100 terabytes of storage, which needs to be sort of protected in the sense that we cannot lose the data. And again, it's and the computation took literally almost a year, in pieces and so forth. And now we are ready to release it to the ecological community with a lot of success. So this is a massive high performance computing problem. The scale of the problem, both in computing and storage, has gone up by more than 6 orders of magnitude since we started back in 2000. And it was a pretty big problem back then. So not to minimize that, it was a pretty challenging thing at that time. I remember receiving those data in mail as opposed to using FTP. So this is but times have things have come very, very far, and it's very interesting and challenging. So the students who work on these get such good experience in working at the high end of the computing that they could go to any company and sort of work on any big problem and not feel like they're working on anything too big from their perspective.
That's great to hear. What do you tell incoming students who want to work in this area? What part of data science and machine learning do they need to know to work on these types of problems in earth sciences?
Okay, so you need to have a really good, strong background in machine learning, data mining, latest advances. And I must sort of say, of course, a lot of things have happened, but a lot of the recent advances, a lot of the work that we use have advanced machine learning, but we end up using some of the latest advances, some of them like papers published last year, paper published 2 years ago. So what I'm saying, it's such a synergy in the sense that we cannot do everything ourselves. And yet, you cannot just simply use the latest advances by themselves. So you have to be smart enough to know what the state of the art is. You have to be smart enough, or you have to be diligent enough to dive into some of these problems, to learn the intricacies. You have to be motivated enough to work with your collaborators, because if you're working on a traditional problems, maybe 3 months will get you a paper. If you're working on some of these problems, it could take you a year, 2 years, 3 years, and you have a product, you have something that would change the world. That's something that will give you very big satisfaction, right? So the rate of production of papers is sort of not as high necessarily, but the amount of learning that you get to do, amount of value that you get to add to your own education, and the amount and the importance that the recruiters give you when they sort of, I have a very large group. A lot of people graduate each year, and some of them, of course, go to academia and continue this environmental work. Right? Most of the rest end up going to working for places like Amazon and Facebook and Google and so forth. And they just love them for this big background in environmental sciences, because they know that these people have solved very, very large problems. So they don't have to go through the regular, the coding process and can you do this, can you do that? Because they sort of want to learn, how did you handle this challenge, that challenge? So it's actually a very nice learning experience, but it's not an easy one in the sense that you have to be committed. You have to enjoy what you're doing. You have to be willing to cross the different boundaries. You have to be willing to talk to the graduate students in the other discipline, because you cannot learn everything on your own. But the reward for you is that not only you get to use the latest and greatest in machine learning, but you also get to advance them in ways that can come back to help the rest of the field.
So there's another question from Martin, and I'll turn it over to him.
Okay.
Hi, Vipin. It's a very long time. I think I last time saw you in one of the SIAM meetings in 1990s when I was still in US.
That's
so
right.
It's really pleasure to hear you again. What worries me a little bit is what I consider a little bit of a tension between you saying we need to all work together, and then in the next statement you say, and I have access to unlimited resources of Google Cloud, probably sponsored by Google. Which means that you have enormous amounts of data and you have enormous amount of computing power. And I'm sorry, but there are very few so fortunate like you who have this enormous amount of data. Okay, data I can probably ask you, and probably you have some data, but access to those resources is limited. So could you maybe very fast point to some sub-problems that are of sizes that can be solved by researchers in Poland, Romania, I don't know, South Africa, India, and other places that have limited resources and would like to contribute? I think that it would be very important to see and hear something in this direction as well. So how can we help not being capable of running unlimited Google Cloud? Thank you.
Very, very good question. So let me address multiple components of this. So one of the other areas that I work on, very, very sort of closely is the healthcare, which also has a lot of data and a lot of interesting societal applications and yet challenges. But the difference between the climate science and the healthcare is that in the healthcare, even if you have data, even if you're sitting next to the data, you are very limited in what you can do with it, because of the HIPAA regulations and such. So one thing that's very easy about the climate science data is that nearly all of it is public and anybody can access it. So that's the first part. The second part that you're talking about is actually very, very important. That is, not everybody can work on a global scale like we're able to do, because that requires a lot. It requires not just a lot of computing power, not just a lot of storage, but also a long history of building expertise. I've been working in this area for 20 years. So the students come, and the next generation students who come, they train the previous one. So basically the previous one generation student train the next one. So basically it's a chain that sort of works. Now, it used to be extremely hard for anybody to sort of walk into this field and do anything until very recently. And I think you have to give credit to companies like Google and Microsoft for making that transition easier. Google, for example, has created a lot of this data that I was talking about is at least available in a processed form in a way which used to, 15 years ago, we used to have to work very closely with NASA to get the processing done. So right now, a lot of the processing is done by the folks at Google, and they make it available freely. The second thing is there are, especially in the US, there are a lot of supercomputing centers that you can get access to. So even if you don't have local supercomputing centers, you can still work outside. Now, the third thing is you sort of say, look, I'm sitting in Poland, I'm sitting in India, I'm sitting in Africa. How do I work on my local problems? To address the third part, then what some of us are beginning to do, and this is a group effort, it's not, none of us is doing it by ourselves, is to have an increasing focus of creating smaller benchmarks. Benchmarks that are terabyte in size, a few hundreds of gigabytes in size, so that these benchmarks become somewhat more manageable, and then people can still do some interesting problem with them. The work in that direction is slow, but it's beginning, and I think you will see more and more of those products out there available to public. So very good to hear from you that just people would like to work globally on it, and it's a music to the ears of some of us who are sort of trying to build these data sets for public consumption. And you will see them coming, in the next year or two, coming in and sort of being advertised through some of these websites and conferences. But again, thank you for asking a very good question.
So Vipin, maybe one more question before we wrap up, and it comes from Wenlong Feng, who says, thanks a lot for Professor Kumar's fascinating presentation. It introduced many topics of remote sensing applications. Is there any progress of data science in regional or global climate modeling?
Okay. So being able to model the climate actually has many different components. One of them is being able to see what's happening to the Earth from an environment from the remote sensing perspective, which is sort of what I sort of covered here. If you recall, in my slide, I showed you the last slide with a whole bunch of different components, and many of those other components dealt directly with the global climate modeling. So I did not talk about that thread, but in the global climate modeling component, the biggest contribution that I can sort of say is that there's an increasing awareness now on a global scale that we have to bring machine learning and these climate models together. So this idea of bringing physics-guided models into the climate modeling is just taking off. If you go to my website, and you will see a workshop that we organized last summer, it's about 8 months ago, and you will see speakers, of course, from multiple fields, including hydrology and freshwater science, but the big component on climate science. And you will see a huge number of people who have talked about the work on bringing machine learning and climate science together. And those talks today remain some of the most visited talks after the workshop was held in August. So there are thousands of people sort of still watching it, and thousands of people attended, of course, in a virtual mode, David, last summer. So tremendous application. I didn't talk about them here, but it's a big area of our focus, bringing physics and modeling together.
So Vipin, I want to thank you again for giving the Yingwu College of Computing Distinguished lecture for the spring 2021 semester, and also the Data Science Seminar Series, and also to all of the audience here who have attended from all around the world. Thank you to everyone as well. And I hope to see you again in person soon. And thank you for doing all of the work that you've been doing.
Thank you. Thank you.